radius of the smaller circle above. Please note that capital R is parallel to lowercase r, and the length between capital R and lowercase r is h, or we call it as a height. Next page. Take a look at this figure. This is just the 2D version of the figure in the previous page. As lowercase r and capital R are parallel to each other, so the theta are the same in the figure, and lowercase r is equal to capital R times cosine theta. Okay. Take a look at this figure again. Consider there is a very little increase in theta, and it will lead to very little increase in s. We will call it d theta and dsc. dsc is equal to capital R times d theta, because arc length is equal to radius times theta. So the surface area of the upper hemisphere is equal to the sum of circumference times ds. Circumference is equal to 2 pi r. So we can integrate 2 pi times r times cosine theta times r times d theta. By some calculation, we can get 2 pi r squared, but remember, we have just calculated the surface area of the upper hemisphere, so we need to multiply it by 2, which is equal to 4 pi r squared. Next page. This is 4 pi r squared. We multiplied it by 2. Okay. Second, we are going to take a look at the derivation of the sphere volume formula, which is V equal to 4/3 times pi r cubed. Next page. Consider this figure again. We are not using cosine theta this time. Instead, we use Pythagoras theorem. So lowercase r squared is equal to capital R squared minus h squared. Next page. As we all know, the derivative of volume is area of a circle. Area of the circle is equal to pi r squared. So let's integrate pi r squared, and r squared is equal to capital R squared minus h squared. So by some calculation, we can get V equal to 2 pi r cubed over 3. Again, we need to multiply it by 2, which becomes V equal to 4 pi r cubed over 3.
Okay, so this is my this is Elias. Yep. So this is proof of how the surface area is equal to the derivative of the volume of the sphere, corresponding sphere. So what we do in this case, we take a existing sphere and we add a small length to the radius, and we give that small length the name dr. So now we can calculate dv over dr, which dv in this case is the volume of the sphere. So with this this new sphere, what we do is basically we press it from both sides, so top and bottom side, so we can get a right-angled cylinder, which is in this case. So what happens is the result of flattening the sphere is what you see on the right, and now we can use the area of the right-angled cylinder, which we know, to calculate its volume. We use the volume, which is 4 pi r squared over 2, to get 2 pi r squared. Then we multiply that by the height of the right-angled cylinder, which is 2 dr. Then we differentiate the result, which was dv. So what we get is 4 pi r squared times dr. Then dv over dr is 4 pi r squared, and we get the proof of S is 4 pi r squared, which that's how we got from the sphere. There was many methods proving the relationship, but we found that this one was the most like best to describe in like models. Now I'll pass this to my teammate.
Yeah. Yeah, hi. So does this relationship hold in higher dimension? Yeah, first we think about in the 2 dimension. The area of the circle, which is the volume of the sphere in the 2D. So the area is the is pi r square. If we differentiate, we can get 2 pi r, which is the parameter. So we can get the relationship is hold in the 2D. In the 3D, we proved in the last question, which is hold. So if we go to n dimensions, so next page. Yep. So in the n dimensions, we can get the volume of the n sphere is Vn, we call it Vn, and the surface area, which is Sn. Now we create is a R, so increase R on the Vn, so which called dr. We also can get dv by dr. So like the surface area of n ball times dr, which equal to the dv. So we can rearrange the equation, so we can easily get the dv divided dr is the surface area. So so we just prove the relationship in the high dimensions. So the answer is yes, is hold.
Anyone have any questions? No? Yeah.
Okay.
Sorry.
So I think it's fine. So can you let me know how many people has spoken? Is it all of you?
Oh yeah, all 3 of us.
Okay. That's fine. So in fact, you are a little bit over the time, but it's fine.
Sorry.
No, that's fine. That's okay.
Yeah, it's fine.
We're being a little bit flexible because of COVID, Arthur.
Yeah, I understand. I just let them know.
Well, congratulations, guys. Thanks very much for doing that. Whoa! I thought that was pretty awesome.
Thank you very much.
Well done. That's a big
Hope it was-
deal to put all that together and present it to your peers. It's very hard, and it takes years and years and years for you to become somewhat comfortable with that whole process. But congratulations to you. So I'm going to pause the congratulations there because we've got to hear from others. So well done, but let's move on. So Kyle, is your group ready to go? Are you here? Okay, Jacqueline, it looks like it's your group.
Wait, I'm in Carl's group, I think.
Okay, Thomas, well, if you want to take the lead with that, I'm happy with that.
Yeah, so we just got a video, so...
That's all right. Away you go. Thank you very much.
Yeah, all right, just give me a minute to share it, sorry. All right, share screen. There we go, it's fun. All right. I'm just gonna quickly test the audio to see if you guys can hear it. Is that okay?
Yeah, go ahead. Yeah.
So can you hear this? Can you hear?
No, I can't. When you share your screen, when you do the share screen, on the bottom left-hand corner, there's a tick box that says Share Desktop.
Oh, okay.
And so when you do share, it's on the bottom, Share Desktop Audio.
Share sound. Yeah, I see it. There it is.
One. Yeah. So if you click that and then you restart, we should hear it.
All right, cool. So I'll give this another shot.
Zeno's paradox.
Yes, perfect. There you go. Well done.
All right, cool.
Which aimed to contest the philosophical ideas of change and motion, which he supposed were an illusion contrary to what an individual believes based off their senses. Zeno's paradox